Welcome to Cloud Wizard. In this video, we're doing a complete deep dive into the design of Netflix, the system that streams 4K movies to over 250 million users across every device on the planet. We'll cover content ingestion, distributed transcoding, global CDN delivery, adaptive bitrate playback, DRM, and the recommendation engine that keeps users watching. Whether you're preparing for a senior engineering interview or building video infrastructure at scale, this one is for you. Let's get into it. Welcome to Cloud Wizard. In this video, we are doing a complete deep dive into the design of Netflix, the world's largest subscription video streaming service. If you have ever wondered how Netflix delivers 4K movies to over 250 million users across smart TVs, phones, browsers, and gaming consoles, with barely any buffering, this video is for you. We will walk through the functional requirements, non-functional requirements, high-level system architecture, end-to-end user journey, core models, low-level design, and the trade-offs that come up in a senior system design interview. Whether you are preparing for a FAANG interview or building video infrastructure, let's get into it. Here is the core problem. Users expect to press play and watch a movie in high definition within a second, no matter where they are, what device they are on, or how bad their network is. But behind the scenes, video files are enormous. A single 2-hour 4K movie can be tens of gigabytes raw. You cannot stream that from one data center to the whole world. You also cannot use the same file for every device and bandwidth condition. Add to that personalized recommendations, multiple user profiles, digital rights management, offline downloads, and real-time playback analytics. The business needs a globally distributed video platform that can ingest content, transcode it into many formats, store it cheaply, push it close to users through a content delivery network, and adapt playback quality on the fly based on network conditions. Let's walk through the functional requirements. First, the platform must ingest raw content from studios and encode it into many formats and resolutions, from low bitrate mobile streams to 4K HDR. Second, it must store those transcoded assets durably and cost-effectively across a global object storage tier. Third, it must deliver video through a content delivery network that caches content close to users and supports adaptive bitrate streaming. Fourth, it must provide a playback service that selects the best CDN, fetches the right manifest, enforces digital rights management, and switches bitrates smoothly as network conditions change. Fifth, it must recommend content by using a recommendation engine that ranks titles based on viewing history, explicit ratings, implicit signals, and collaborative filtering. Sixth, it must support search, user profiles, watch lists, downloads, and playback resumption across devices. These capabilities make the service not just a video player, but a personalized entertainment platform. Now the non-functional requirements. Playback latency must be extremely low, with time to first frame under a few seconds and rebuffering kept rare. Availability must be extremely high, because users stream around the clock and expect uninterrupted entertainment. The system must scale horizontally to support hundreds of millions of concurrent streams and exabytes of video storage. Global distribution matters, so every major region must be served from nearby edge caches to avoid cross-continent latency. Cost efficiency is critical because bandwidth and storage bills are massive at this scale. Security and privacy are essential because the platform handles paid subscriptions, viewing history, and licensed content protected by DRM. Finally, the system must gracefully degrade, for example by dropping bitrate during congestion rather than stopping playback. Here is the high-level system architecture. On the left, content providers upload high-resolution masters to an ingestion service. Those assets are stored in a global object store and sent to a transcoding farm, which produces many variants per title in different codecs, resolutions, bitrates, and container formats. The transcoded files are pushed to a content delivery network composed of thousands of edge servers around the world. When a user opens the Netflix application, the client talks to an API gateway, which routes requests to services like authentication, user profiles, the catalog service, the search service, and the recommendation service. At playback time, a playback service selects the best CDN edge, returns a streaming manifest, and coordinates with a DRM license server. A playback analytics pipeline collects events such as starts, stalls, bit rates, and viewing completions to feed recommendation models and operations dashboards. The key metrics to memorize: cold time to first frame, the delay from pressing play to video appearing; rebuffering ratio, the percentage of playback time spent waiting for the buffer to refill; average bitrate, which measures the quality actually delivered under real network conditions; CDN cache hit rate, the fraction of requests served from an edge cache rather than the origin; recommendation click-through rate, how often users watch a suggested title; completion rate, the percentage of users who finish a movie or episode; availability and error rate, which capture how often the service fails to start or fails during playback; cost per stream, a crucial efficiency metric given the scale of bandwidth and storage. These metrics are what engineering and business leadership actually track. Let's trace the end-to-end user journey. A user opens the Netflix app on a smart TV. The home screen is populated by the recommendation service, which ranks titles based on her profile, recent watches, and trending content. She selects a new series. The client requests a playback manifest from the playback service, which authenticates the user, checks the subscription, and returns URLs to CDN-hosted segments, along with a DRM license request. The client starts downloading the lowest bitrate segments to begin playback quickly. Then the adaptive bitrate algorithm switches to higher or lower bitrates as the network allows. Halfway through the episode, she pauses and later resumes from her phone. The same profile, progress, and preferences follow her across every device. Behind the scenes, analytics events feed the recommendation engine for the next session. The core models and algorithms. The content catalog stores metadata about every title, including titles, genres, cast, subtitles, audio tracks, and regional licensing rights. The transcoding pipeline defines a media processing graph that produces ladders of bitrate and resolution variants. A video manifest, such as an HLS or dash manifest, lists the available segments and bitrates for the client to choose from. Adaptive bitrate streaming uses throughput estimation and buffer occupancy to decide when to switch up or down in quality. The recommendation model combines collaborative filtering, content-based filtering, and contextual bandits to rank personalized rows. The CDN topology model maps users to the nearest healthy edge using DNS or Anycast routing. The DRM license model controls who can decrypt what content on which device. The key trade-off is quality versus latency. Higher bit rates look better but need more bandwidth and more buffering. Now the low-level design deep dive. The playback service is stateless and handles millions of concurrent sessions. It receives a content identifier from the client, fetches the manifest from a metadata cache, selects the optimal CDN edge based on geography and current load, and issues a time-limited signed URL for the segment files. The manifest itself references multiple bitrate variants, and the client uses an adaptive bitrate controller to pick segments. The media storage layer is backed by an object store with lifecycle policies that move old content to cheaper cold storage. The transcoding service is built as a distributed job queue. Each job is broken into parallel tasks per resolution and codec, with retries and idempotency. The recommendation service uses a feature store to serve pre-computed candidate sets and a ranking model to order them in real time. The database layer uses a mix of key-value stores for session data, wide column stores for watch history, and search indexes for content discovery. Key takeaways for your interview. First, Netflix is fundamentally a content delivery and personalization problem. So start with ingestion, transcoding, storage, CDN, and playback before jumping into recommendations. Second, adaptive bitrate streaming and CDN edge selection are the most important mechanisms for a smooth user experience, so be ready to explain manifests, throughput estimation, and buffer-aware switching. Third, DRM is non-negotiable for licensed content, so mention license servers, key rotation, and device attestation. Fourth, recommendations drive engagement and retention, so discuss candidate generation, ranking, the feature store, and A/B testing infrastructure. Fifth, cost and efficiency matter at scale. So bring up transcoding ladders, storage tiers, cache hit rate, and cost per stream. If you can walk through this system with these 5 points, you will signal strong senior-level design thinking. That's it for Design Netflix. If this helped, like and subscribe, and I'll see you in the next one at Cloud Wizard. And that's a wrap on Design Netflix. We covered the full picture, from studio ingestion and transcoding ladders, through global CDN delivery, adaptive bitrate streaming, DRM, and the recommendation engine that powers personalized rows. If this video helped you, please hit that subscribe button and the bell icon so you never miss a new system design video. Drop your questions in the comments below. I read every single one. See you in the next one at Cloud Wizard.